So I actually pretty much only do real-world projects. And I think this stuff with embeddings over the last 5 years is probably the area of neural networks that's had the biggest actual impact on industrial applications that are of the form of being very stochastic processes. So trying to predict someone's customer lifetime value or whether they'll churn or what they'll do next on your website are all extremely stochastic problems. And they're not very well suited to kind of having end-to-end learning because they're so noisy, and end-to-end learning is it's a sort of point process estimate thing. So I think this stuff is really, really important in industry at the moment. There's 4 sections to this talk. So I'll start off just by explaining why learning representations is such an important thing in machine learning, and how if you don't do it right, things go horribly wrong. And there are loads and loads of pitfalls if you just represent your data in the wrong way. And embeddings it's just such a nice and easy concept to represent data in a very compact and efficient way. So it's really cool. And then I'll explain how people learn embeddings. So the word embedding, it's kind of overloaded. So lots of different people mean different things by it. So some people say that when you do matrix factorization for a recommender system, you're learning embeddings. Some people refer to an embedding as being like any set of weights from a neural network. In this talk, I'm specifically talking about shallow neural networks of the type of word Tyvek, if you've heard of that. So there's very specific type of embedding, which is incredibly popular right now. That originally became important as a way of representing words, and in fact is a core part of Siri, a core part of Google search engine now. But was so incredibly popular that it's spilled out into representing pretty much any types of categorical object you can imagine. So graphs, human beings, products on websites, pretty much everything has had the embedding treatment applied to it, and pretty much without fail it's made the application better. And the last part of the talk, if I get there, it's a bit more esoteric. So I'm talking about some research that's come out only in the last year about how, well, I'll just leave it at that. It's new research in this field. I'll talk about it if we get there. Cool. So the problem of representation. And this is the question of how, given real-world objects, do you get them into your machine learning algorithm? And the example I'm using here, because I work at ASOS, it's around this data set where you have the height of some people and you know which type of shoe they're wearing, and you're trying to predict whether they're a man or a woman. And it's pretty easy to represent height because it's just a number. In this case, I've just sampled these things from 2 bimodal Gaussians, one from a man and one from a woman, so they overlap a little bit. But the question is that how do you represent shoes in an efficient way so that you can predict gender? So one thing you could do is you could just take all of the shoes and assign them an index. So you could take the first one you pick up, you could say that's going to be number 1, the next one you say that's shoe number 2, next one shoe number 3, and so on until you've listed all the shoes out. Sorry. So that's one idea. That unfortunately doesn't work very well because your machine learning algorithm will think that shoe 1 and shoe 2 are very similar, or that shoe 3 and shoe 4 are very similar, and that shoe 1 and shoe 20 are very, very dissimilar. And if you just randomly chosen those numbers, you really don't want to be pushing that information into your algorithm. And so what people do is they say, okay, well, let's make everything maximally dissimilar. So let's do this. Let's put things on completely separate axes, and let's have a 20-dimensional space to represent all of these shoes. And that's a perfectly valid thing to do, and it's in fact what I'd say almost all machine learning practitioners do. But it has a lot of really horrible effects. So it means that everything is now maximally unsimilar to everything else. So what if there's a better way of representing things where you don't have to massively blow up the space, and you can make similar things close to each other? And that fundamentally, that's what an embedding is. So here I've taken the 4 shoes that are in this data space, and I've embedded them, and I'll come to how you embed them later. And what you find is you can represent similar things with numbers that are close to each other, and dissimilar things with numbers that are far apart. And that actually makes, well, that's really good for three core reasons. So if you're trying to do something like classification downstream, right, classification is basically about taking one type of data and drawing a line to separate it from another type of data, and drawing another line to separate it from another type of data. It's a geometric thing. And if you take that first representation, where you just randomly assign things to indexes, you can't draw a line that separates men and women in that data set. So you have this data point up here, which you can't separate from the others. But if you choose a clever embedding where similar things are close to each other, magically, it's just the same data set, but you get linearly separable data. You can classify that data perfectly. So using embeddings makes downstream classifiers work better. If you're clever about representing data so that similar things are close to each other in your vector data space, your embedding data space, then machine learning works better. Another reason to do this is it's much more compact, right? So we all pay money for computing space. This here is a one-hot encoded representation. It requires a lot more bits to store data like that, and a lot more neurons if you're going to put that into a neural network, than storing data like this. This is the embedded representation. It's much more compact, way less bits, much faster to read, much faster to write. And the final reason that pretty much everyone agrees that this is a clever thing to do is something called the curse of dimensionality. So the curse of dimensionality is a very well-known concept in machine learning, where the higher dimensionality you get, the more data you need to learn anything. And that grows exponentially. So for every extra dimension, you double and double and double. It's a really, really bad thing. So you don't want to represent categorical variables with 20 dimensions, or if it's words, 100,000 dimensions, because then it's almost impossible to learn anything. And all points become equally far apart. There's this weird phenomenon. If you take like a 100-dimensional orange, all of the volume is in the peel, right at the edge of the peel. So high dimensions and like good machine learning algorithms really don't mix. You want, if possible, to be low dimensional. So that's why we want to do embeddings. They're compact, so you save space. They're low dimensional, so you avoid the curse of dimensionality, and they just produce better results because they put similar things close to other similar things. So how do we actually learn these things? The idea is really simple. So you randomly assign a vector to all of the things you're trying to learn. So in this case, shoes, but it could be words, it could be customers, it could be products. And then you have some process for iteratively pushing similar things close to each other and dissimilar things away. So you can think about it, if you're interested in physics, it's kind of like attractive and repulsive forces kind of iteratively acting, and you do this millions or billions of times, and eventually you end up with this vector space where similar things are kind of clustered together. So in this diagram, kind of things with high heels are on the left, and things with booty things are kind of at the bottom, and slightly more manly things are at the right. So you end up with a kind of semantics of the objects that you have, basically, if you execute this process correctly. So what you need is a random initialization of these vectors, and then you need some process for pushing similar things together and pulling dissimilar things apart, and that's it. And the efficient way that people have worked out you can do this is using a neural network. And this is basically the simplest neural network you can imagine. It has a single hidden layer. So it's not actually a deep network. People call this deep learning, but in this case it's a shallow network, and it has one hidden layer. And it has all of these neural weights here. They make up a matrix, and a matrix is just a collection of vectors. So this guy here, his representation is just the weights he has to this hidden layer, right? So this is his vector representation. In this case, it's 5 dimensions. And when you train a neural network, you randomly initialize the weights. So that's just randomly putting all of your shoes in a vector space. And you choose the dimensionality that you want to learn the embedding in just by choosing the number of hidden layers. So that's how you randomly initialize it. And then whenever you train a neural network, you need a loss function. That's basically it. You need a loss function and an architecture. And then magically the thing will train itself to find good weights to minimize your loss function. So the question is now, what is the loss function that learns a good embedding? And this is all about something that has been known for maybe 40 years in natural language processing called the distributional hypothesis. So the distributional hypothesis says that if two words are constantly co-occur together in the same sentence or within a short distance of words, then they're similar. So what people do is they take enormous chunks of text, and here I've got a little sample, so where there's a will, there's a way. And they define a context window to say anything within this context window, we'll call it similar. And then you try and predict a target word from the context words. So you have a loss function, which is happy when you're predicting will from all of those context words, and is unhappy for every other word in your vocabulary, so for every other word in the 100,000 words you might have in a vocabulary. And you phrase this as a prediction problem. A lot of, I think almost all of the kind of big advances in machine learning over the last 20 years have been thinking about things as prediction problems instead of counting them or kind of doing descriptive statistics. So for 20 years, guys were doing NLP by counting, doing word counts and kind of comparing these things and doing frequency diagrams. And then Yoshua Bengio turned up and said, hey, wait a minute, why don't we try and predict which word will occur next after, say, 9 words? So that was the context. And then a little bit later, guys were like, well, actually, we don't even need to predict the next word, right? What if we just predict any word, the middle word or the context words? Then we can learn a representation that's able to predict things. And here I just highlighted a little bit of the maths. This is the only equation in this talk. But in this equation, these kind of V's are the embeddings, right? So this is the embedding of one word, this is the embedding of another word. And this thing here is an inner product. So in all of the maths, these embeddings only enter in an inner product. And this is so what you're trying to do is predict this output word from all of these input words, just using these representations. And once you have that, you put it into the kind of neural network architecture. You use GenSim or TensorFlow or whatever you like. And stochastic backpropagation just takes care of finding embeddings that make words that tend to co-occur frequently in your text similar in the embedding space. And it turns out that these operations, this stochastic backpropagation, it's just a load of linear vector operations. So the vectors, you randomly throw them out there to start with, and they just linearly update. So you're just moving representations around the vector space until things start to clump together because words tend to co-occur together, or customers tend to co-occur together, or products tend to co-occur together. So this stuff had been known since about 2011, this idea of training a neural network to predict words in a context window had been known about for a while, but this didn't really take off until 2013 because it's not really useful if you require 100,000 computers in 4 weeks to train a decent embedding model of words. But around 2013, some really, really major advances were made. So this model here, sorry, this one here, that's a softmax predictive output, and it requires a sum over all of the vocabulary. So for each kind of pair of words that you think are similar, you have to sum over every word that isn't in that pair. So 100,000 operations for every pair of words. And if you have 1 billion words, then there are 2 choose 1 billion pairs. And that thing will take the rest of your life to run. Okay, so it's not a lot of fun. But what people realize is that you can do something about that terrible softmax. So the softmax is, it's order of the vocabulary. And Jeff Hinton and a guy called Andre Mni, who's now at DeepMind. Hinton is at Google and the father of deep learning as well. Realized that you could change that to a log n operation. So a lot faster by changing that softmax into a hierarchical sort of tree type structure. It's a really beautiful idea. They've got an amazing, highly cited paper about it. However, it's hardly used anymore because there's a much, much simpler idea which works faster and gives pretty much the same results, which is instead of calculating for all 100,000 words in that big softmax, just take the 2 that actually happened and then sample 5 that didn't happen. And that seems to work almost as well. And so that's what everyone does. That's called negative sampling. And that was, again, this guy Mni at DeepMind. So that's how he built his reputation, those 2 big papers. And now this stuff, it's genuinely amazing. It's like 1 C file or 1 gensim file in Python, and you can put 1 billion words in there on your laptop, on a laptop exactly like this, and it will run in an hour, and it will give you word embeddings, which is really kind of stunning to get that level of performance on such easy hardware, completely open source. So anyone in the world can now do this and do it for anything, and I'll get to that in a minute. But that's part of the reason why it's so popular. The software is really, really efficient, and it runs really fast on a single laptop. So when Thomas Mikolov, who's the guy who created Word2Vec, first got famous, he was at Google, he came up with this really efficient implementation, and he wrote some great papers, published at NIPS and various other places. And this was the killer slide he had in his paper. He said that these neural representations, they seem to learn something about the semantics of words almost magically. So in this diagram, what he's trying to show is that the vector difference between Italy and its capital, Rome, is roughly the same as between Greece and Athens, is roughly the same as between Spain and Madrid. So there seems to be this vector algebra here that understands meaningful, important things about the world that you never told the computer. And everyone's kind of like, whoa, that's amazing. Neural networks must be doing something incredible. And there's this other, I wonder if my laser works. Not really. So then this is a thing people often say. They talk about this vector operation. If you take the vectors that represent queen, king, woman, and man, it turns out that king plus man minus woman, the closest vector is queen. And again, people were like, oh my God, this is just insane. Like, how is this happening? And it got a lot of hype, and this paper got thousands of citations, as it rightly should have done. And only a few years later did people realize that actually this had nothing to do with the neural network. And a lot of people don't realize this, even kind of practitioners in the field, even researchers don't realize this. So you get exactly this same stuff just by using the sparse representation. And by the sparse representation, I mean if you have a context window and you pass it over a load of text, and say I have a context window that includes like the, and, bat, and man, you put like in the column, you put a 1 for and, bat, and man, and you keep doing it and summing up, so you tally up all these numbers. You end up with this enormous, every word has 100,000 dimensional representation, which is a count of other words that co-occur with it. Well, if you do that, it's horrible, it takes a really, really long time, and it produces a useless representation. But you get this and this. So there you go. So just to refresh the timeline again, 2003 was when Yoshua Bengio introduced this idea that we should be predicting words rather than counting words. 2013 was when Thomas Mikolov wrote the Word2Vec paper, which was certainly the most influential paper in machine learning that year, I'd say. And then suddenly people realized that, wait a minute, all we need is that C file, which is open source, and a sequence of anythings that obeys the distributional hypothesis. So if you remember, the distributional hypothesis just says that things in the sequence that co-occur frequently are similar. And then like in half an hour, I can learn an embedding of anything. And that means I can get an academic paper out of it. And there were then maybe, I would say like 150, but probably like 10 times more papers that weren't getting accepted, written, called Node Tyvek, Customer Tyvek, Product Tyvek, Item Tyvek, Hyperproduct Tyvek. It was kind of embarrassing a little bit going around and seeing all these things and all these posters, but I wrote one, so yeah, so just to go through these things quickly then. The most influential one was done by Leah Mikolov, and that was extending the idea of representing as a vector a word to an entire document or a paragraph. And they did that by using a sort of hierarchical representation. All of the papers are referenced here. I think I'll these get given out afterwards as well, so if you want them. So that was the kind of the end of the playing around with words thing. And then this guy called Brian Perosi, who just actually won an award for his PhD thesis at KDD this year, he came up with this idea of deep walk, where you walk around a graph and you collect the vertices that you travel through and you make a sequence out of them. And then that obviously obeys the distribution hypothesis, and therefore you can embed nodes of a graph, so you can embed users of Facebook or Twitter. And then there were a couple of other sort of more derivative papers along that line afterwards, like Line and Tyvek. This was done for products, so for the Amazon product customer graph. It's been done for fashion styles by a group of researchers at Zalando, which is a big competitor of ASOS. It's a terrible paper. It's not really, no, it's a good paper. We did it for customers of ASOS. So we have a paper called Customer Lifetime Value Prediction with Embeddings, which I will talk about as a case study in a second. And then it was done by a couple of teams, weirdly, for iPhone apps. So you can embed iPhone apps based on like the order you either view them or the order you download them. But literally anything where there's a sequence of tokens that repeat themselves, where you expect things that co-occur in the sequence often within a certain window to be similar, can be embedded. If you have the data, it will take you an hour. So it's a cool thing that's just very much like human scienceable, which is nice, because a lot of stuff right now isn't human scienceable. A lot of stuff you need 1,000 GPUs. So this is the idea that Brian Perosi had with Deep Walk. So he imagined a random walker on a network, and the vertices are numbered, but they can be labeled with anything. And then this guy just sort of walks around completely at random, and as he walks across a node, you add that to your sequence, and he keeps going, and you add these things to your sequence. And then you end up with a sequence just like Word2Vec. And so what he did is he said, okay, well, I'll take 80 walkers starting on each of these vertices, and they'll all walk for 50 steps, and then I'll have this massive, great big data set, and I'll embed that. And it turns out it improves like loads and loads of things you can do with predicting attributes of people from their social networks. So if you want to predict their age or their income from Twitter users or their lifetime value from, say, an ASOS network, all of those things are improved by using the embedding you learn from the graph, rather than, say, the raw features like who you follow or what your age is. So it's a really cool application. This next bit it's a little case study on how we specifically at ASOS have used embeddings to make our customer lifetime value prediction system better. So it's only a few slides, whereas I sometimes do a talk that's half an hour on this. So I'm sorry if I kind of brush over it quickly. I'm around for the rest of the day. If anyone's like genuinely interested in lifetime value prediction at ASOS, then feel free to ask me some questions later. This should be a video, but I think the video is not there. So I'm going to try and show you the video.
ASOS is a global fashion destination for 20-somethings. We do more than just sell clothes. We provide fashion
so
advice,
optimistic,
produce video content.
What have I got to do? God, I can find it for you. Huh. Oh, so I need to just end show here. This is risky live. Okay, I'm not sure this is going to be worth it for 1.5 minutes of ASOS video, but
ASOS is a global fashion destination for 20-somethings. We do more than just sell clothes. We provide fashion advice, produce video content, and a magazine. But how do we know what these intangible products are worth? By predicting the lifetime value of our customers. This allows us to measure the impact of watching a catwalk video or reading a blog post, enabling us to properly attribute the marketing channels which truly drive our sales. Predicting customer lifetime value is an old problem. There have even been competitions to find the best approaches. We mix the old with the new, automatically generated features with handcrafted features. With over 100,000 products, we have billions of customer product interactions. They form an extremely large and sparse matrix that is difficult to use in its raw format. We overcome this problem by learning neural embeddings where each product is defined by the sequence of customers who interacted with it. Using these sequences, we learn an embedded representation of our customers. Customer embeddings last longer than product embeddings and can be used for forecasting. Customer embeddings capture not just the value of products, but also the diversity, newness, and boldness of their taste. These are all important characteristics for predicting high-value fashion customers.
Go ASOS, and we're recruiting. Okay, great. I'm just going to give a quick overview then of that project that we did at ASOS and how we used embeddings to make things work better. And I'll just have to give you some background. So this might be kind of boring, but otherwise how we used embeddings bit won't make any sense. So our model it's a random forest model. It had 128, 135 handcrafted features. So we took things like the average spend last year or when you were last on the site, all that, basically everything we could think of. And it started to asymptote after a while, right? So we added a new feature and it basically made no difference. And even if we thought it was a really clever feature, it made no difference. And that's quite a common thing that happens when in industrial machine learning projects. And this is how we set it up. So we trained it, we have a feature periods, and then because it's lifetime value, there aren't any real labels. So we just said like what you spent over the last year was your lifetime value minus returns. So we trained a random forest here, and then this is the live system where we relearn all the features from the last year and we predict what someone's going to spend over the next year. And the reason these things are disjoint is because if they weren't, we'd be leaking information from the training period into the test period, which we obviously don't want to do. And then we learned an embedding from the products that customers viewed. So we have 80,000 products on the site. For every single one of those products, we created a sequence of customers that interacted with them, so viewed them in this case. And as hopefully I've been able to communicate over the last half hour, the second you have a sequence, and you expect it to obey the distributional hypothesis, an hour later you can have an embedding. And so that's what we did. And our thinking here was that customers that view the same product are likely to be similar because they have sort of similar tastes. And also customers that view products like really soon after they come on the site are quite fashion forward and therefore quite high value. And then customers that kind of all come in at sale periods or when an item gets marked down, they're quite cost sensitive and therefore might not be the highest value customers. So that's why we thought this would make sense. Skip over that slide. And then we just added the embeddings as features to the model. So we had a random forest with, these are the top features, but there were 135 features. And then we just added another 64 features from the embedding. So we learned embeddings of customers in 64 dimensions, and each dimension became a feature of the random forest model. And even though we were properly asymptoting in terms of performance, this bumped the performance up by a decent chunk. I think it's something like 30 basis points, which we hadn't had for our last 50 features or something. So it made a very large difference, and it allowed us to incorporate the enormous viewing behavior matrix that we had, which we had no other way really of incorporating into our model without aggregating it. As it happened, no one had done this before. No one has used embeddings for forecasting, and there's a really good reason why no one's used embeddings for forecasting. So if you were paying attention during the video, we said that customers last longer than products, and so can be used for forecasting. And that's really important because embeddings, they're not like other features, right? So they're not like how much you spent over the last year. But that has a name and a label. So when you learn a parameter for it, you can just look up what parameter was attached to that thing and just apply it in your test period. But embeddings don't have a label, right? They're 64 dimensional, but they flip around, right? So if you learn the parameters of these guys in the training period, you don't know where they are anymore. They move around randomly when you retrain from scratch in the test period. And so you would be applying the wrong parameters to the wrong dimensions, which is why no one had been using embeddings for forecasting before. And so what we worked out you can do is as long as you have tokens, in this case customers, that are around in the training period and also in the test period, you can warm start the embedding. So remember I said to do an embedding, you randomly initialize some vectors, and then you move like ones that are similar together and ones that are dissimilar apart. Well, actually here we kind of didn't do that. We took the embeddings from the training period of the customers that were present in both periods and initialized the new set of embeddings with those, therefore maintaining the meaning of the dimensions. And then we initialized all the new ones using interactions with the existing customers so that we guaranteed that our embeddings didn't switch around. They stayed in the same place. Okay, that doesn't happen in this diagram, but they stayed in the same place. So we solved that problem effectively by warm starting them. There was actually a paper at iClear this year by Babylon Health where they faced exactly the same problem. They wanted to do translation between English and Spanish from embedding to embedding. And what they did is they took words that were the same in English and Spanish, so things like information and information, and they learned a linear map between them. So there's two approaches that came out. This is a 2017 KDD paper that we wrote to do that. But now embeddings can be used for forecasting, so that's really cool. I have, I think, maybe 8 minutes left. So this next section, probably some of you will not find particularly interesting. So this is the cutting edge research in this space. And it's about new geometries. So remember that these embeddings are in a vector space. And there are actually lots of different types of vector spaces. And the one people always use because it's the one you know is the Euclidean vector space. But actually there are like 3 isometric spaces in the world. So this is the Euclidean one. It's flat. It obeys Pythagoras' law, and it has dot products in it. So the inner product is the dot product. But then there's a spherical one, which is like the surface of the Earth, which is, again, quite familiar. And then there's this kind of weird one here, which is hyperbolic space. So hyperbolic space, you can think of it as being like a saddle. So at all points, space curves away from you instead of curving down. It's a different kind of isotropic space. And one way of thinking about it is in terms of triangles, right? So if you imagine playing baseball, if like it's 300 yards to the edge of the, I don't know what you call that, the home run bit, and 300 yards across in Euclidean space. If you're in spherical space, it'd be 300 yards, and that would only be like 100 yards. And if you're in hyperbolic space, it's 300 yards, but that distance is like 1,000,000 miles or something. So everything gets really big, really fast. Actually, it gets exponentially big as you go out. So space expands much faster in hyperbolic geometry than it does in Euclidean geometry. I'm going to skip over these 2 slides about Euclid's postulates. Oh yeah, but there's one really important thing about hyperbolic space. So it doesn't have just 2 parallel lines can intersect many times. So these lines are all parallel to this line, even though they all go for a single point, which you can't get from Euclidean space. And this is a crochet version of it, the knitting version. I don't know who does that, but someone does that. Okay, so why is hyperbolic space, why do people care about it? And the reason people care about it is because it is the continuous analog of a tree. And that's really, really important if you're trying to embed something that looks a bit like a tree, right? So and a tree grows exponentially. So if you're trying to embed something like a Facebook social network, that looks a bit like a tree. There are some people that have a huge number of connections. They're the top of the tree, people like Justin Bieber. And there are some people that have no connections, like me, at the bottom of the tree. And if you try and embed that in Euclidean space, it's absolutely impossible. So in 2-dimensional Euclidean space, you can't embed like one popular person with 4 friends who aren't friends with anyone but the popular person. It doesn't fit in the space. But in hyperbolic space, you can embed that one popular person who has 100 million followers. That embeds perfectly. A perfect embedding is called an isometric embedding. So it embeds isometrically in the space. Words have the same property. So some words are friends of everyone. The word the is friends with everyone, right? It co-occurs with every other word pretty much. It's so popular. The word and is friends with everyone. It co-occurs with every other word. The word hippopotamus is friends with almost no one. And so words have this same property. They're kind of like a tree. They're hyperbolic. Their geometry is hyperbolic. So word Tyvek is a cool idea, but it's in the wrong geometry, I would say. This is like a wicked diagram. I really liked this before I found out what it was, and now I really love it. So this is an MC Escher sketch called Circle Limit 3. So he's a like famous lithograph guy. He does these steps where you keep going up and you always end in the same place. And this is a visualization of hyperbolic space. It's the Poincaré disk. So these objects are all the same size in hyperbolic space, but they get infinitely small to the edge because hyperbolic space gets infinitely big to the edge. It's bigger than Euclidean space, and this is infinity in hyperbolic space. It's really nice. And so, how long have I got? 2 minutes, good, I'm glad. And also it turns out that it's really, really easy to hack Word2Vec or GenSim to change it from being in Euclidean space to being in hyperbolic space or to being in spherical space or any space you want. I would say hyperbolic space is the right space for these kind of objects. And so all you do is, if you remember earlier I said these vectors only exist in the inner product. Well, in Euclidean space, the inner product is the dot product, which is just take every component and times it by every other component together like that. And if you just switch that up to being the inner product of your own geometry, you get an embedding in that geometry. And so that's all we did. We wrote a paper about this. So we just changed this inner product to be this polar hyperbolic geometry thing. And the only other thing you've got to do is, because you're doing stochastic gradient descent, you have gradients, and TensorFlow or GenSim or whatever think that those gradients are being calculated in Euclidean space. So you just have to hack around a little bit to make them know that you're now in hyperbolic space. So for our work, this is just an R in Euclidean space, and it becomes shine R, the hyperbolic cosine function in hyperbolic space. And here's some results. So these results on the left are from my last paper. So these are loads and loads of networks. And what we're doing here is we're saying, okay, if you know the labels on some of them, so let's say you know the labels on 50% of them, can you predict the other 50%? This is the blue lines are in hyperbolic space, embeddings in hyperbolic space. The red lines are embeddings in Euclidean space. And these embeddings are between 2 and 128 dimensions. Remember, you don't want high dimensions. These embeddings in 2 dimensions. And they win almost every time in just 2 dimensions compared to 128 dimensional Euclidean space. And you can't really see this, but if you could, you'd see that the colors split. So the white ones and the black ones split, and this is just kind of random noise. Lots of people are looking at this now. So this diagram here is from these guys at Facebook AI Research. So they applied this to something called WordNet, which is a graph of words, and they showed that if you do these hyperbolic embeddings, you get things like mammals in the middle and rodents, and you see the hierarchy of animals just by embedding WordNet in hyperbolic space. And the last thing I've seen is this big paper here by a guy called Michael Bronstein, and it's co-authored with another guy called Jan LeCun. You might have heard of. He runs Facebook AI Research, but he's also one of the 3 fathers of deep learning. So he's now doing research in the space as well. Michael Bronstein is coming to Imperial too next year, so that's cool. Great, so that's everything I wanted to talk about. Just to summarize, I spent a little bit of time talking about why representation is so important in machine learning and how you can mess it up. And then I discussed how neural embeddings are learned, at least in the Word2Vec kind of meaning, and how you can really, really easily apply that to any kind of categorical data where you have sequences that obey the distributional hypothesis. I talked a little bit about a case study where we did this at ASOS, and then I just wrapped up with an extension to new geometries, so hyperbolic space. Thanks.